Hi everyone, welcome to the video. Today we are going to solve node at a distance. So in this question, we are given a binary tree with a number of nodes and a distance k. We have to return all the nodes which are at a distance of k from the leaf node. So see in example 1, 8 is one such leaf and we have to and k is 2. So we have to find any node which is at a distance of 2 from this leaf node. We find 3. 3 is at a distance of 2 from this leaf node 8. Then again 4, 5 and 7. 4, 5 and 7 are the leaf node. We have to find any node if there is any node which is at a distance of 2 given over here from these leaf node 4, 5 and 7. Yes, we have one. We have one in that case, but okay, there are three paths which leads from leaf node to the same node with a distance of 2. In this case, we will count it as only one, and one was from 8, and one was from this 4, 5, and 7 combined. In this case, we have two paths. Similarly, for example, 2. Okay, k is 4, and leaf node is 9. Okay, so in both the case, it will lead to the similar path. Hence, we will take only one. Now, I'll solve this question using BFS. Okay, I will just do a BFS traversal of this binary tree and to find all the leaf node. After that, we will identify nodes which are a distance at k from the leaf node and return the count of all such unique nodes. Okay. So first of all, I will use a DQ from collections code DQ. Okay. I've used DQ. I've imported it. Okay. Now Q equals to DQ. You may be wondering what I'm doing over here. So I have initialized a DQ. Okay. Okay. Then this DQ is populated with a tuple, okay, which contains the root node and an empty list. Empty list represents path from the root to the current node. So empty list represents path from the root to the current node, and another list path to leaf. Okay, path to leaf, which will which is initialized as an empty, but will store all the paths from the leaf node. Okay, now while this queue, while there are element in this queue, we will traverse. Okay, we'll do a BFS traversal. Okay, while queue is not empty, we will we will figure out two values, leaf and a path. Okay, leaf and a path. So that queue got of left. Okay. In each iteration, now it dequeues a node and its corresponding path from the queue. Okay, now if the node has a left child, we will append the tuple of left child and a current path, adding to the current node of the queue. Let's see how it goes. If node has left path, in that case queue dot append node dot left, well, left child along with along with left child, okay, along with path path plus the current node, path plus the current node of the queue, path plus the current node of the queue. Similarly, for the right side, if this node has a right child, then we will append right child along with path plus current node, path plus current node. Okay, path plus current node. So we took the path of the left child, of the right child. Now we will have to check if we have reached the end, we have reached the leaf node. Okay, if you have reached the leaf node, okay, if you have reached the leaf node, that is there will be no further left or right child. Then we'll append the complete path. We'll append the complete path from the root to the leaf node to the path to leaf list which I have created. Now if not dot left and not dot right, which says If there are no left child, no right child, which suggests that we have reached the end, we have reached the leaf node. In that case, this path to leaf will append into it path plus node. Okay. Now we are bending the complete path from the root to the leaf node. Okay. From the root to the leaf node. Again, we will create a result set. Okay. Set because we have to return only unique as we saw in the example one. Okay. Now we will do a traversal for E in R2 leaf. Now we will do a traversal for all the paths from the leaf node. Okay. From the leaf node because path to leaf store all the path starting from the leaf node. Okay. Now for each path, if length, if the length of the path is greater than or equal to k plus 1, why I'm taking k plus 1? Because we have to include leaf node also. See in example 1, we were taking 8 as a leaf node, and at a distance of 2 we are having 3. But if you count all the three, take all three, 3, 6, and 8, it will lead to k plus 1, that is 3, because k is 2 over here. If you'll include the leaf, you will have k plus 1. Okay. In that case, we are taking the leaf. We have entire path from the leaf. That is why we are taking here k plus 1. Now for each path, if the length of this path is greater than or equal to k plus 1, if length of this path is greater than or equal to k plus 1, okay. Okay, so why k plus 1? Because it indicates that it has at least k plus 1 node, which has at least leaf. Okay, now we'll add the kth node to the result set. Yes, dot add. Okay, we added it. Now this set will ensure that each node is counted only once, regardless of how many times leaf path is at a certain distance away. Okay, let's return length of the result, which will tell us if okay, you'll return the length of the set result, which will represent. Okay, there's some issue. What is that from? Okay, there's a spelling mistake. At the end, I just return the length of the result. I will iterate y, so it will return the function. Okay, return the length of the result, which will represent the number of unique nodes that are at a distance of k from the leaf node. So as you see, our solution is able to get executed in very less time. Okay, and give us a pretty easier time complexity. So I will again iterate that we have used a BFS traversal over here and I'm maintaining a queue. Okay, DQ, double-ended queue. So I hope you learned the concept and enjoyed it. Thank you. Have a nice day.